Okay, good afternoon. You all are doing well. We're going to start off today with a little bit of group work. Okay. Well, if you give me just a moment, I should be able to get it up for you. So if you are virtual, you can find this in D2L. It is under interactive assignments. And it's also now on your screen. So the Dropbox is already there. And then in addition to the Dropbox, you can so you can download, it's in that Dropbox if you want to download it and do it on a tablet. I will send you up in a moment. If you're in the class, I have paper copies for you. All right. So give me a 5 in the chat when you're ready and you've got this copy down or you've downloaded it, the PDF. Allie is the only person ready. Come on, folks. Oh, good. Anthony. There's some group work back there. Want to find a group to work with. Hey, Max and Cheyenne, you're probably seeing D2L right now. Quiz. Go. Okay, so I posted, oops, that probably won't be very helpful. Let's try that again. Maybe that will be helpful. All right, I've seen the same thing twice. So you can log in there or I'll reshare it. Please give me a 5 once you are ready to head off to Could you find it now, Brian? Hey, Natalie, I screwed up. The exam starts when class starts. So go study. Go find Dallas. He's floating around. All right. Okay. So I'm gonna go ahead. If you are virtual, you need to write the names of your group. And their favorite city to visit. For full credit, so include the name of your group members and their favorite city to visit. Brian, I'm gonna put you in another group since Ray has not joined. You guys are really quiet. Is that thinking or confusion or? What?
No one wants to admit.
Nobody wants to do it? Y'all are still salty about the ECE exam? Yeah. You're working together? Your brain's starting to hurt a little bit?
Oh, yeah.
All right. Say hello in the chat if you all are back. The class informed me that they wanted to do this problem together. This is an unapproved problem. Brian, did that link work? Hey, Lorenzo. Group work is back there. You want to grab it? We're getting ready to go over it. Oh, you followed my keystrokes before I posted the link? Oh, okay. All right. So let's start off by maybe giving ourselves some steps to do this problem. So I was getting some confusion looks in the classroom. Would that be a good place to start with this? All right. So we want to determine the force, right? Or after a force equation. All right, so let's talk about some steps when we're dealing with the problems in this class. The first step is to draw your free body diagram. That's going to be very important for this one because we want to actually solve for the force, don't we? All right, our second step is to determine coordinate system. Looking at this problem, which coordinate system should we be working in?
Polar.
All right, we're going to work in polar coordinates. All right, so that means the sum of the forces in the R direction need to be then m acceleration sub r. The sum of the forces in the theta direction is then going to be m a sub theta, and the sum of the forces in the z direction is then going to be m z. Now, for this problem, it says that we only have motion, in the horizontal plane, so this is not going to happen, correct? Right, let's go back and look at that wording. Motion is in the horizontal plane. So we don't need to worry about any acceleration happening in the z plane. So we're only in the r and the theta plane for this one. Okay. All right. So what else do we know? Well, we know that since we're in this particular, we're working with this coordinate system, we're going to have to be able to find those accelerations, correct? So our a sub r is then going to be r double dot minus r theta dot squared, and our a sub theta is then going to be r theta double dot plus 2r dot theta dot, right? Those would give me my two accelerations, won't they? All right. Okay. All right. So we know our mass, correct? So let's see what we're given. We're given the fact that the mass on this equals 0.5 kilograms. All right. By the way, when we do this, and I don't know if I made this clear, when we do this, these are now our kinetic equations. So we had our static equations, and these are now our kinetic equations. Okay. So what else are we told? Well, we're given that our R value is 0.8 cosine of theta, and the units on that is in meters. And this tells us our theta dot equals 3 radians per second. All right, so let's talk about what forces are acting on this guy here at C. All right, so we have this little collar. This is my free body diagram. And let's go ahead and draw the rod like that. Hang on, let me redo that. So I've got the part that's going around the circle, right? And then we have a rod with a collar being connected to it. All right, and this is my point C. Okay, so let's go ahead. This rod being connected, I'm going to draw my XY coordinate system at that particular angle, which is given to us, by the way, that we want to know what's going on at theta equals 45 degrees. And I think Lorenzo and I talked in the past that it's almost like that's the instant in time that we're interested in. If I said we had a time equation, right, that would give us our interest in time that we want. All right, so if we're drawing this at an angle, right, you told me Right, you told me that we were gonna be in polar coordinates, so we're going to have our axes as r and theta. There is a normal force acting on this. All right, and that's often by 45 degrees. We also have a force coming in. You okay?
Yeah.
Right. We also have a force coming in on from the rod of the arm. So that becomes our free body diagram. Now, let's go ahead then and talk about how we can solve this. This is the normal force, by the way, of the collar. All right. So if we sum in our R direction, I don't know what happened there. It started and then it didn't go. All right, that's going to be our mass times A sub R. So is F going in our R direction? No. Is N sub C, does it have an R component? Yeah, it's going to have an R component. So this is then going to be negative N sub C, cosine of 45 degrees equals 0.5 kilograms times my acceleration in the R direction. You doing okay, Logan?
Yep.
You're Alicia, right? Skylar. Okay. All right, she's in the other. Sorry about that, Skylar. F of theta then is going to equal MA sub theta. How many equations do we have dealing with the theta, or how many unknowns should I say do we have? Well, we have the force, correct? That's along our theta axis. We then have the normal from the collar, sine of 45 degrees. That's then going to equal 0.5 kilograms A sub theta. All right, so let's go ahead. How can I find our A sub theta and A sub, oopsie, I screwed up. No, I didn't. Oh, I'm okay. Sorry, I've been up since 1:30 local time, so I'm a little tired. All right, so how am I going to find these? And we had these equations. I posted those on the other page, didn't I? All right, and they were the fact that A sub R equals R double dot minus R theta dot squared, and A sub theta then equals R theta double dot plus 2R dot theta dot. Okay, so let's go after our A sub R equation. A sub R is R double dot minus R theta dot squared. Well, let's see what we know. We know R is 0.8 cosine of theta, correct? So we're interested when theta equals 45 degrees. So, why don't you go ahead and run a calculator for me? 0.8, make sure you're in degrees and not radians. And what do you come up with when you put that in?
0.57.
Equals 0.57. All right. theta dot was given to us as 3, right? This is given to us in radians per second. And then we need to find R double dot. So R is 0.8 cosine theta. R dot is then going to be, cosine is a C, so you change. 0.8 sine of theta, theta dot. Did I do that right? And then we're gonna have theta double dot. All right, so we're gonna want to take then the derivative with respect to time. I'm gonna pull the 0.8 out just to get it out of my way. Negative 0.8, we're gonna take the derivative with respect to time of sine of theta, theta dot. We had to use chain rule to get to that. What do we have to use now to get our R double dot? We're gonna have to use what? I'm multiplying two things together. Yes, Anthony, product rule. All right. 0.8, what are we then gonna have? We're gonna have sine of theta, theta double dot, plus cosine of theta, theta dot, theta dot. All right. Okay. So we can plug all these numbers in. We know, back up just for a second, we know theta dot equals 3. So theta double dot has to equal what?
0. But we only know that because it says it's constant, right?
Yeah, it said it's constant and it told us what it was, right? If it had given us theta was an equation, then we'd have to go through the same development to figure out what it was. Does that make sense?
If it doesn't say it's constant, if it just gives us a number, we know it's constant.
Yes.
Okay.
Yes, you can make that, you can safely make that assumption. All right. So our R double dot is, the first term's gonna go away. All right, so we're gonna have negative 0.8 times cosine of 45 degrees times 3 squared. All right, the first term went away because theta double dot is a 0. So what do you get when you put this in? Negative what?
Negative 5.09.
5.09?
Negative 5.09.
All right. Okay, I think we have, oh, let's make sure we deal with this one. If we put this one in, this one is then going to be negative 0.8 because we're going to need all three of these numbers, aren't we? And then we're going to have sine of 45 degrees times 3. So negative 1.69.
Negative 1.69 for this one.
Okay.
For that, yeah.
Yeah, negative 1.69. I have actually negative 1.67. All right, so let's figure out now what our A sub R has to be. We just found all the pieces for it. We know the original equation, R double dot minus R theta dot squared. So R double dot was negative 5.091 minus, we figured out that R, did we ever calculate out R? I don't think so either, so,
Yeah, 0.566.
oh no, we did. It's right there.
Oh, okay.
Yeah, you got it. All right. Minus, what'd you get? 0.566.
Yes.
All right, times R3 squared. So that becomes then negative 10.18 meters per second squared. Right, now we can find RA sub theta. That's R theta double dot. That's very convenient because that's going to go to 0 plus 2 R dot theta dot. So this is 0.566 times 0, 2 times negative 1.6971 times 3. And the end result here is the same. Anyone else get those two results to be the same?
Yes.
That's
So let's figure out what our n sub c is. Because we know negative n sub c, that normal force, cosine of 45 degrees keeps the whole thing from flying away. That's going to equal 0.5 times negative 10.18. And n sub c, I ended up with an n sub c of 7.2 newtons. Anyone else get that? This, by the way, came from summing our forces in the r direction. Now, if we sum our forces in the theta direction, right, what are we going to get? Well, we're going to get F minus 7.2 cosine of 45, right? That's going to end up being 0. Sine of 45 degrees equals 0.5 negative 10.18. All right, so our force coming in from the center is then going to be 0.
I was doing the calculations and stuff, I got like a very small difference between AR and theta. Do you think
Okay.
that's just like a rounding error?
Could be,
It
could
ended
be,
up-
or it could be the way, yeah, it could definitely be a rounding error. What's the small difference that you got?
It was like 10 to the negative 15.
At 0. All right, Atreyu, how are we doing?
Good.
Let's make sure we review the steps that we did for this problem, okay? We drew our free body diagram. We drew it in terms of, but our axis became R and theta because that was the information I was given, correct? All right. Okay, so then we then did our kinetic equations. So when you take your next exam, you're going to want to use your kinetic equations. That's the whole point of chapter 13, right? If we were doing it as normal and tangent, it would be then a sub n and a sub t, wouldn't it? Right. And then then we had to find our a sub r, which primarily involved taking some derivatives. We were able to plug it in and then solve for n sub c, and then ultimately solve for f. Okay, big picture, yes.
You originally said that that's the F of
The collar, is that the same as the F of the arm that we wanted?
Yes, yeah. Yeah, because this is moving around, so it's gonna have that force is then gonna be in theta. N sub C is coming in from the normal force from the collar.
Can I see your A sub theta equation, please?
What do you wanna see?
The A sub theta.
Equation?
Did you use R dot or R? Or 2R theta dot? Just because in my notes I have it as R, not R dot, so I wanted to be sure.
Oh, okay, let's double check that. It should be 2 R dot theta dot. Okay. It is weird. Well, because the bar is when this moves, and that was why you did the pre-class quizzes about stuff moving. When this is moving, the force involved is going to be an angular force, right? That's where the acceleration and the force involved, it's going to be angular. All right, as this moves, it just, for lack of a better term, what's it going to do? And that right here, it's at an angle theta. Here it would be at a different angle. Here it would be at a different angle. Here it would be at a different angle, wouldn't it? So that's why the force needs to come in along the theta axis. All right. So we're gonna have to move forward into chapter 14. I screwed up. Your chapter 14 pre-class quiz does not have the diagram associated with it. So I will get that posted for you. All right, so we're gonna start, and those of you that are also in thermodynamics, right? We're gonna start talking about work and kinetic energy, and what else do you think we're gonna have to start talking about? Potential energy, right? So, as I said, we're gonna start in by talking about work and kinetic energy. All right, and then we'll move into potential energy. And then we will move into, we'll have to do conservation of energy, and then we will move into momentum and impulse. All right. So are we awake and ready to go? Let's start off by talking about work. All right. From a standpoint of physics, what is work? Basic work.
Force times distance.
Okay, so our physics class taught us that it's going to be force times distance. We're going to need to start to think about it a little differently, and that is energy transfer. What happens if I have a displacement, fancy word, distance, right? Equals 0, nothing moves. What happens then? Then we have no work. All right, what if I have negative work? Now, this is a little different than our thermodynamics definition when we have negative work. In this case, if work is negative, energy is being removed from the object, okay? But that means the force is in the opposite direction of the distance. And so what you were supposed to do in your pre-class quiz was you were supposed to look at an illustration of a car. Okay. Okay. Illustration of a car. If I apply, this is the direction the car is going, correct? So that's my displacement S. But what would happen if I apply the brakes to the car? Then what type of force are we going to have? We'll have a force going this direction, won't we? So that's why we would end up then with a negative work. All right.
Dr. Meehy?
Yeah.
Can I go back to the displacement equals 0? Aren't there some situations where you moved and then you moved back, so there was 0 displacement, but there was work done?
So what you're going to do in those situations is you're going to look at them as two separate. So back in calculus, you did problems that look like this, right? So you would calculate work from there to there, work from there to there. As long as the force is going in the same direction as the displacement, it's going to be positive, right? So in thermo, right, even if we come back to 0 when we do our PV diagrams, we still have work involved.
We lost heat.
Because we lost heat. All right. So here we're going to look at it from a force perspective, not from a heat perspective. But it's a similar thing. You know, this would be
There's friction involved?
yes. This would be force 1, force 2, and this would be force 3. So my work would then be force 1 S1 plus force 2 S2 plus force 3 S3. And we probably would have to take absolute value, but you would count because the work and the distance, the S is going in the same direction, it's going to all be positive work. All right, does that make sense? Okay, so I know you did these displacement is 0, but that means nothing's moving. Okay, which we're not going to see. Okay, so here are two types of work that we're going to be dealing with. All right, so you told me work was force times distance. And by the way, work in your textbook, because you got to be different, right? They use the symbol U. I don't know why. That's what your textbook is using. So to keep confusion as confusing as possible, we will use U. We're going to then define work as the change in work is then going to be force vector dotted with dr. All right, so now you notice we have a dot product. We also have this image here that shows that we're dealing with an angle theta for cosine. If you remember, and these are sort of, if you remember the dot product, right? If I have a dot product, let's just take F dot R, that's going to be magnitude of F, magnitude of R, cosine theta. Agreed? I don't know if you remember the dot product or not. Do you remember the dot product, Christopher? Okay, so what's happening here is if our force is constant, if we integrate that guy, and so we're looking at work from 1 to 2, and I'm not crazy about it being U either, but we'll all get used to it. That's going to be F sub C cosine theta integral S1 to S2 ds. And for most part, except for the whole cosine theta stuff, that was what you told me, that it was force times distance. All right, it would be wonderful if our entire problems look like this. Do you think they're gonna look like this? What's your guess, Skylar? Skylar says no. Brian, do you agree with no? Instead, we're gonna look at work as a variable force. All right, so now our work from 1 to 2 is then going to end up being, we'll have S1, S2, F cosine theta ds. All right, if, by the way, if theta is 0, then that's just 1, right? And then we're back to force times distance, aren't we? Which is what you've been used to doing in the past. Sorry, Skylar, did I move that? So they're under the assignment tab. And I can make sure they get loaded either in the pre-class quiz under content, or I can load them in the assignment tab themselves. I know 13.1, is that one I uploaded? Anyway, one of them I know got uploaded into it, but I might need to finish setting up those pre-class quiz drop boxes. Thank you, Brian, for bringing that to my attention. I'll get you extra credit for that. All right.
Is this formula wrote here for the U1 to 2 the same as the one that's up above?
No, it's not, because FC cosine theta in the one up in this one is a constant, so I pull it out of the integral. Whereas here, it is no longer a constant. All right, it's a function of S. So it needs to live inside, it's going to be inside the integral.
Theta's not constant either.
It could be. But in theory, both of those could be not constants, so to speak. All right, so I mentioned earlier that when we talk about work, it's a transference of energy, correct? You guys know about 2 types of energy. What are they? Potential energy and kinetic energy. All right, so we're going to look at how work then deals with basically potential energy. So once again, because we don't believe in using standard variables, because why would we do that? All right, U in this class is what? Work, right? I mentioned that you probably should have first couple of pages of your notebook should be your cheat sheets for this type of information. Now, T is going to be kinetic energy. That didn't need a pin drop. The good news is we're still going to define kinetic energy as 1/2 mv squared. So that at least is positive. Okay. The principle of work in energy is the following. If I start with some kinetic energy, and I then add work, or if your work is going, if the force is the opposite direction, I subtract work, we're gonna have what? We're gonna have our new kinetic energy. That's not spelled right. That one's spelled right. All right, so equation wise, we're gonna have T1, our starting kinetic energy. Now, if we're starting from rest, right, T1 would just be 0, wouldn't it? No, you're not allowed, so you're not allowed open book on the exams because all equations are given to you, Brian. But when I call the cheat sheet in the notebook, what I've explained in the past that something you ought to consider doing is both Valerie and Atreyu, Christopher in class, for example, they're taking notes here. They're taking notes in like a spiral notebook, right? And so this is my spiral notebook that I use for class planning. So this is what's happening this week for me in my 6 classes. But you take the first 3 or 4 pages, use it to write down equations and definitions. All right, and if you, because every class you take might have a different expression for kinetic energy, or not expression, but they might have a different variable. And it's just one of those little things to help you track your variables in your equations for a particular class. Those of you that are taking thermodynamics, kinetic energy is KE in that book with Morin, right? No, you should not use any notes. I hope you didn't use any notes on the first exam because you should not use any notes for the first exam. All right, we're going to add to this our work. All right, and so that's then going to be the sum of the work. We'll say it's work from 1 to 2, and that then is going to equal my second kinetic energy. All right, because kinetic energy because this is squared, kinetic energy is going to always be positive. Right. And once again, we know work is positive based on or negative based on its direction. When we are dealing with weight, all right, so when work has to do with weight. Now, you'll see problems in your homework where you are launching stuff. Your homework is you're launching, where'd my homework go? We're launching bricks. We're not launching anything in that one. We're not launching anything in that one. It's just moving. We've got a spring and a steel ignet that we are launching, 2 springs and a block that we are launching. Here we are sending a block down a ramp. All right, and so we also then have, so weight could potentially create some of your work. And so the weight could be a plus or a minus. All right. It is considered, think of it as backwards, positive when going down. The other work, so as I said, your homework problems, and we'll work some problems in class today, but your work, if you are, for example, one of your homework problems, you have a roof, you have a brick on the roof, you launch the brick off the roof, right? The force on that brick being launched, no notes were used and you were in good shape. The force on the brick being launched has to deal with its weight, doesn't it? All right. So, and since the brick is going down here, UW from the weight is going to be positive work. Alright. For a spring, and I mentioned you have about 3 problems involving springs, we're gonna use our spring constant. So we know the force of a spring, we always refer to it as Ks, where K is a material property, correct? Alright, so the work U sub S for a spring is then gonna be Ks, that's the force, times S, which is the distance. So that becomes Ks squared. If we have multiple springs, we will have to add them together or add and subtract. All right. How are we doing so far? Give me a 6 if we're doing okay at the moment. I have some folks holding up 6 fingers in the classroom. That's awesome. They're with you Zoomers in spirit. All right. So Valerie mentioned this. We're also going to have to worry about friction. We've dealt with friction. Have we dealt with friction in this class? I think so too. All right, but I know we had a little bit of friction at the very end of statics. All right. So let's talk about how the equation is going to look for this particular scenario. Okay, so what's going on here? I have velocities heading off that way. The minute I see I have velocity involved, what do we know? We know we have kinetic energy. So we're always going to go back to this equation. We have our first plus the summation of our work is then going to equal our second one. All right, if this is at 0.1 and this is at 0.2, this is going to end up what? 1/2 mv1 squared. We all agree? Sorry, Logan. Can you see it now?
Yeah.
Get this out of the way. All right, let's talk about the work that's going to have to be involved. Notice I'm putting a force P on it. All right, that could be a tension, it could be a rope that I'm pulling. All right, if you think about it, there was some, I don't know, TikTok, Instagram, I don't pay attention, where you grab your kids' feet and they put on glasses and then you grab their feet and pull them out of the frame. You guys remember seeing that? All right, that's what's happening here. All right, and so is that P going in the same direction as the block is traveling? So we're going to have to add up our works now, right? We're going to have PS because we have a force P traveling in the S direction. Now, we might end up having to integrate to get P if P is a function, correct? All right, then what do we have working backwards? Well, working backwards, we then have our normal force. U sub K N sub S, right? Normal force to S, that's going to equal then 1/2 mv2 squared. So that's how we're going to put these types of problems together. What is the difference between UK and US? We used US. What?
Sorry, don't, we also need to multiply that by S since it's work, not force.
Oh, it's not N sub S, it should be NS. So it should be UK, you're absolutely right. And capital S. Right?
S is the displacement.
Yes, S is the displacement. It's negative because it's going in the opposite direction. Okay, does that make sense, Logan?
Yeah.
All right, it's UK. Yes, Andrew, I'll get you credit for that too. What else do we know? It's UK because it's now kinetic friction. We have done work back in statics with US. US was our static friction, right? UK is then kinetic. All right. And then someday you can get into amazing problems where you have stuff moving. I don't even know what class they teach this to you in, but you would have stuff moving and then your UK would not be constant because it would heat up. Right? So as it's heating up, as it's moving, you're gonna get something different. When they put their foot on the brake to squeal their tires and move out of an intersection, what are they doing there? They're building up a lot of what? Heat, right? That's gonna then transform itself into energy to push that car forward. All right. It's actually kind of stupid because it does kill your tires, but no one asked my opinion about it. And I know nothing about looking cool, so I just don't worry. Let's spend some time with an example. So I'll be quiet for a moment while you guys either take a screenshot of this or make yourself a note. All right, and so give me a 7 in the chat when we're ready to move through this problem. Got a few folks in class still writing. Skylar's already solving it, but a few other folks are still writing. Be careful and make sure I drink water, mix water with the tea today, because that is cup number 6. Okay, we good? Drew? How are we doing, Skylar? We're good? Got some 7s in the chat. Thank you, Ali, Anthony, and Andrew. Melody, are you ready to go? All right. So what's happening here is we have a 1.5 kilogram block and it slides against a smooth plane. Those are key words. If it's a smooth plane, what is that telling us? No friction. No friction. Okay, so if it's a smooth, it might be super, super small friction, but F equals U sub K times N is going to equal 0. Strikes a nonlinear spring, with a speed of V equals 4 meters per second, the spring is nonlinear because it has a resistance. So I was talking about work of the spring being Ks squared. This problem, we're actually told that the force of the spring is Ks squared, where K is 900 Newton per meter squared. Determine the speed of the block after it has compressed the spring, S equals 0.2 meters. All right, so what's going to happen with our free body diagram, right? Well, we're going to have what going on? We are going to have force here of our spring. All right. We are going to have the weight of the block. By the way, this is given in kilograms. So if it's given to me in kilograms, what do I multiply by? Well, 9.81, right? Pounds we leave alone. There's also going to be a normal force. But is the weight and the normal force going to affect the work done on the block? Not for this case. The block is not falling off a building, is it? All right. The block doesn't have any friction, so we don't care much about the normal force. So what do we know? We know our kinetic energy is then going to be, plus the sum of the work is then going to equal, for lack of a better term, our final kinetic energy. And we want to find what? Speed of the block after it's hit the spring. So what speed is this, V1 or V2? All right, this is going to be V2. We're actually given V1 is 4 meters per second. So this is going to be what? 1/2 mv squared. We're going to have to talk about how to calculate this. Equals 1/2 mv2 squared. That's what we are solving for. All right, we know this. This is going to be 1.54 squared. All right, that's a number. Hopefully we're all comfortable with writing this down. Now, let's talk about the work involved. The fact it says non-linear means we're going to have to take an integral. If it's linear, it's a constant. It's non-linear, it's not a constant. The spring is going opposite the direction of the block. Do we agree? Block is traveling this way. Spring is pushing back that way. So it's going to be negative. All right. So we're going to have negative integral S1 to S2. All right. And then this in here is going to be my KS squared ds. So, and that's then going to equal 1/2 1.5 V2 squared. So Valerie is now saying, wait a minute, you said work was KS squared, but in this case, this is given to us as the force of the spring. All right, and it's nonlinear. So that word nonlinear triggers integration must occur. If it's linear, then it's a constant, right? We don't need to integrate. All right, so I don't have these numbers written out individually. 1/2 times 1.5, which is 3/2 times 4 squared. That's going to be 12, isn't it? Yeah. All right, minus, now it tells us the S, so this is going to go from 0 to 0.2. K is 900. We're then going to have S squared ds equals, and then over here we're going to have 3/4 V2 squared. I'm just turning that 1.5 into a fraction. All right, so this is going to end up being 12 minus, and then we're going to have here 900 S cubed divided by 3 evaluated from 0 to 0.2 equals 3/4 V2 squared. By the way, if you put that integral in your calculator and came out, sure, Anthony, came out to have an answer, right? I'm gonna write the answer down real quick. V2 ends up being 3.58 meters per second. Would that be legal on an exam? Of course. Okay. Anthony is asking me about the fact that why is it negative? So Anthony, would you agree the distance of travel of the block is heading this way? Would you agree that that's the direction the block is headed? All right, but the force spring is going to be pushing on the block this way, correct? So that's why it's negative, because it's going opposite of the direction of the block. All right, so that's when work becomes negative. All right. Y'all do some homework. All right, I will, please turn in your group work in class or online. Please say hello in the chat. I will use that to take attendance because we're out of time. And the static students are hovering like sharks because they want to take their exam. I don't know if they want to take it, but they're hovering. Well, okay, Brian, we look at the direction of travel and then we look at the direction of force. If the direction of travel and force is the same, the work is positive. You can think of it as going to go faster. If the travel and the direction of force is opposite of each other, the work is going to be negative. All right, guys.
Scroll down.
Oh, sure, no problem. Let me know where you want to be.
All right, there.
Okay,
Thanks.
you're welcome. You're welcome. All right. There's some pre-class quizzes up here and I will reprint out and I will repost. Thank you, Logan.
Right now.
Yeah, yeah. Thank you. Skylar, you don't have to do that, but if that helps you learn. Okay, if it helps you learn, then that's good. Right, because the point you can take it. The point is just, I just want to make sure you learn, and I don't know, I mean, if you have to think about something. Right, right, if you have to think about something, then I think it helps you learn. Make sure you say hello in the chat and then you're dismissed.